Welcome back everyone. We are talking about mathematical foundations of geometry and topology, and we have made quite a bit of progress starting from set, then we talked about topological space, and then we talked about manifolds, and manifolds are the sort of real means the physical topological space which we care about, and all the physical process in this universe happen in manifold. And manifold differs from topological space is when you can, roughly speaking, coordinatize it. So, that means you can have a homeomorphism which is a structure preserving map to RD, right. So, that we will call a d-dimensional manifold. And then we have talked about how to define a directional derivative on a manifold, which is nothing but defining the tangent space, tangent vector, and acting on any function. And then we also define that these tangent vectors at a given point on a manifold forms a tangent form a vector space, and then for a vector space you have a unit vector which the kind of frame bundle or the unit vectors of any vector space. And then we also talked about the cotangent space, which is the dual space, so that we can define the length of vectors or unit vectors. Then also we talked about tensors. So, now we will introduce the another kind of a space called bundle. Okay. So, again I will start with what it means roughly, and then we will give the more mathematically concrete definition. And roughly speaking, and as I always say intuitively, is that a bundle is something that we have already talked about. So, let me start with that, which is a manifold together at every point having another space. And let me start with a tangent space that we talked about. So, at every point of this manifold we had a tangent space, and if you go to another point you will have another tangent space, and there will be unit vectors and so on. So, at every point you have another space attached to it, and together M and this tangent space at all points we define something called a total space, and that is a bundle, and for this particular case it is a tangent bundle. Okay. So, now let us generalize this idea to bundles, and then we will talk about we will come back to tangent bundle and fiber bundle and so on. So, a bundle is where at every point on a manifold we can add same or different objects, and going beyond tangent space we can even add real numbers, complex numbers, even group, vector space, Hilbert space, and so on. And that is roughly what we have done here. We just added different things at different points. It does not necessarily have to be the same, and even if we can have same, but then it can have a there can be differences within the complex number matrix and so on and so forth. And together, and these things which will consistently draw in a vertical line will be called fiber, and at every point a fiber is defined of a manifold. So, together called bundle. Okay. So, that gives you a rough idea about what is bundle, and now be a little more specific about what is bundle. So, bundle consists of three objects, three things: a total space denoted by E, and a base manifold. So, this is the base manifold which we are writing as some sort of a vertical horizontal space, and a projection and a bundle projection map. What it does is that at every point, so what it does is that it takes you from the total space, which is roughly this entire space, fiber and base manifold, to a to the manifold. If you do it in a given point, elements to elements, it will be taken to a given point. So, that is the projection map. Okay. So, this cartoon can be slightly misleading. The idea is that it takes you from the total space to the manifold, not just the fiber to the manifold. Okay. And this is a surjective map. So, that means you can have many points from there taken to a single point, or another way to say, at a given point on the manifold I can have many elements, space and so on and so forth. Okay. And the point where you are doing it is called base point, as we denote here. Okay. And this is the base manifold is what we define. And then the fiber is kind of the opposite, but because it is a surjective map, so it does not necessarily have a inverse map. So, and as we introduced earlier, when you do not have an inverse map, so for any point, if you want to go back to under this map, if you want to go back to where it comes from, we will define something called a pre-image. Okay. So, that is what the fiber is. So, it will take you to the space or many elements of that space and so on. So, for a bundle which is denoted by this, three things: base manifold, projection map and total space. At every point we define fiber over a point, base point, as the pre-image of this point on the total space via this map. Okay. It is kind of the opposite, but not the inverse, and that is what we call fiber. All right. This definition is clear. So, since pi is a surjective map, so pre-image is a set or space, can be even group, depends on the thing we have. Okay. And I gave you, we started with one example, which is that the tangent space itself is a fiber space. So, fiber is a space. So, that is the thing, or can be a space, or for us it will be, for our purpose it will be the Hilbert space. So, that is what I wanted to emphasize again and again, that it is not just a point. For us it will be the wave function, and wave function lives on a Hilbert space. And again what we will be interested in, something called principal bundle. So, what is principal bundle? Principal bundle is, and often we denote by P, has a fiber which is identical to the structure group. So, structure group is a group, and let me just give you the example rather than defining it completely, and from the example it will be obvious what it is. So, it can be a kind of a vector space in which you rotate the unit vectors and your vector remains same. So, that means you have a ON group, orthogonal, or n is the number of vectors you have, right, like angular momentum and so on. And you can even have SON, this the special orthogonal group, or U1, which are for the complex numbers, and wave functions are usually U1 or UN, unitary group, or SUN if you have spinors and so on. So, what we are getting into is that, so the fibers, the principal bundles are the fibers where there is a kind of a group structure among the elements, and if you have a group structure, for example, vector space, Hilbert space. So, the elements we have, which will be like a wave functions or vector, one should be able to expand it in the basis vectors or the basis states. Okay. So, and that is going to play a crucial role as we move forward. Okay. So, the bundle is clear, and the essential part is that the reason we really do not want to just put a field or tensor at a given point, because if we are generally going to work with non-trivial manifold topological space in which even the wave functions can differ between different points, and the vectors can differ between different points, maybe they are oriented differently, and as well as your wave functions do have the phase arbitrariness. So, that means as you go from one point to another point, in principle they can acquire different phase, but there is a restriction, and this is what we are coming into. So, now we want to do the calculus on a bundle, right. We did the calculus on the manifold, now we have to do the calculus on the manifold, and that is what the covariant term comes from. Covariant means we want to do calculus on bundle, whereas the directional derivative we did, which is written here, it's was kind of take a tangent vector on a curve at a given point on a function. We did it on a function, and this is what the directional derivative was defined to be. Okay, just a tangent vector. But now we want to do covariant directional derivative, which is a derivative on the fiber. And remember, this is not a function. This can be a space. So, how do we do the derivative on a space, and what additional structure we have to keep in mind. Okay. So, it is always good idea to take example to begin with, and then we can formalize it, and for us we will probably not formalize it completely, but we will do it enough to get you the complete idea about how this covariant derivative is. Okay. So, as I alluded, so fiber is different from functions, it is a space. For example, it is an Hilbert space is what we are interested in, and any element of this fiber. So, fiber, this entire space we tend to write as a vertical line, just a schematic way to represent that this is just not a one point sitting here, but this entire space is sitting here. Okay. And then any point of this fiber is called section. Okay. And we are interested in a section, and wave function is or a state vector is kind of a section in a U1 bundle. U1 is the all the states that you can define, which are related to each other with a unitary rotation or a phase. Okay. So, a single vector in the fiber space is the section. Okay. So, for example, if I have a tangent bundle, a given tangent vector is a section. Right, this entire thing is sitting here, but we take only one vector. Or if you start with SON or orthogonal ON, it is like the angular momentum or classical spin vector will be another example, just one vector, not the entire space is the section. And eventually we will be interested in wave functions. So, wave function is a part of a U1 bundle. Now, what is the important thing about a state vector or a fiber which differs from the function that we have to define a covariant derivative, and here it is. A section which so what I am going to define is general, but we will use this notation to connect you to the quantum mechanics, but for anything else it will remain same. So, what will remain same is that a section can be expanded in a basis states. For example, if you started with the vector can be defined in the frames, in the unit vectors, and angular momentums also can be expanded into Lx, Ly, Lz, and S can be defined into Sx, Sy, Sz. In any sort of vector can be angular momentum can be defined in whatever the frames we have. The same thing about wave functions, I mean, a similar thing. And how do you expand? We have a choice of basis, and generally we take energy eigenbasis or can be something else, momentum basis and so on, and then you will have the components along those bases. This is how a state vector will be defined. psi n, and n is the number of states you have. Okay. And now the things are going to become clearer that this is a function. So, when a derivative acts on a function, it should act on like this, but a state vector is more than just a function, you also have this unit vector. So, how does unit vector change as we make an infinitesimal change from one point to nearby point to define a derivative, and this is what the covariant derivative will play a role. Okay. So, we want to define a covariant derivative on this function or this section that we already discussed. And now, a covariant derivative combines two derivatives. One is on the fiber space, and when you said on the fiber space, we rather meant on the unit vectors. Okay. So, any point, if I think of taking a derivative, I have to define how the things are changing from this point to some nearby point, right. I want to define a derivative, covariant derivative from this point, and I will have two components. So, what we will be doing is that, and I want to do it along this direction, so it is a directional derivative. One will be along this direction, which will be defined by the tangent vector. So, this will act on the function part of this section, which as we had defined in the manifold, and that is called horizontal space. Okay. So, any sort of covariant derivative on section can be decomposed into two. One is horizontal on the manifold, roughly speaking, another is on the vertical, which is along the fiber direction, and you can always do that, right. Any sort of a vector, we learn that we can always put it into an orthogonal, put it into a longitudinal direction, transverse directions, and parallel directions, perpendicular directions. So, here roughly speaking, that is what we are doing. One is along these directions, which is act on the function, and then another one will be on the fiber part, and this is what is called horizontal space. There is a mathematical well defined way to characterize horizontal space, but we do not want to go into that. And the other one is the vertical space, which will be how this derivative is acting on the unit vectors, how the unit vectors are changing. Okay. So, what physically it tracks? It tracks how the fiber rotates, how the unit vectors are changing, how your coordinate system is changing as we go from one point to a nearby point, right, and how the basis states are changing. And they have changed because of the internal structure or the structure group, because the section that we have, it belongs to a structure group. Whereas, in the horizontal space, which is on the manifold, the derivative tracks the physical transport of the particle in space or space time, and whatever the base manifold it is, or could be even phase space, depends on how we define, right. So, now what we will do is that we have two derivatives to track. Rather, what we will do is that we will take this derivative part and put it on the horizontal space, so that we will have one derivative on the physical space or manifold to deal with. So, how do we do that? We define a connection on top of this derivative on this function, which will already track down how the unit vectors are changing. Okay. We account for the vertical space derivative on the horizontal space via connection, and vector field and Berry connections are going to be the examples, but right now this is general. And how do you do that? So, again all these derivatives are much easier to define on a chart, and we have already defined some chart which will be some mu running from 1 to d, and assuming that this is a d dimensional manifold, and there are all the points are mapped to some x1 x2 all the way to xt, okay, and we have already done that. So, we will denote a covariant derivative by this gradient or nabla with v denoting that, and v is supposed to have these two subscript, but we have sort of eliminated those for simplicity. So, along some curve and at a given point, which are all implicit in this v. So, this is a covariant derivative along some tangent space, along the tangent directions, and we can expand it in a given chart, and these are the components, the tangent vectors, and these are the unit vectors which we want to act on the psi, and psi is now expanded into the basis states. Okay. And how do we do that? All right. So, this one now can be written as the components and the covariant derivative along those unit vectors, right. Is the covariant derivative about the total vector, and in a component wide, then this covariant derivative will go into your partial derivatives along each directions with the components, right. And this is the one, then we want to now act on this, and we can use the chain rule. The first, this one acts on the functions or the components, the unit vector, and then this will acting on the unit vector. It is just a simple chain rule. We keep it the way it is, and now this is the one. So, what it has done is that, as we know the definition of a derivative, it is a difference between how the these unit vectors are between two neighboring points. So, I have some unit vectors here, and we make a small infinitesimal change, and how the unit vectors has changed. So, no matter it is always the same structure group. So, even if the unit vector has changed from here to there, the new one we can always expand into the old one, right. So, we are talking about a derivative from this point to that point, and here let us say the unit vectors are rotated like this, E1, E2 and so on, and now we were calculating at an infinitesimal point, and maybe the unit vectors have rotated by E2 or the vector has rotated. So, what we can do is that this much change. So, each component I can again expand into the original one, even this component I can again expand into this component, and that is precisely what we have done here. So, this is the new vector which we are expanding into the original ones, okay, and these are the coefficients. So, these new ones I am expanding in terms of the original E1, E2 and EM, and M runs from 1 to whatever the dimensions of the Hilbert space, and A are the matrix, and it tracks the mu along which directions the derivative is done, and that is called connection. And I will tell you again what it means physically, but mathematically this is what it is. It just tracks down how the unit vectors are changing, and then you are sort of bringing back to what it was with the coefficient. Okay. So, now we can substitute it. So, this is what this terms remains same, and this term becomes like this. So, this is what it will be, and what we can do is that we can exchange the dummy indices m with n. Okay. Nothing else is done, it is just the dummy indices are exchanged for convenience. So, what we will do now is that, so at every spatial coordinate, chart coordinate mu, I have a matrix that is sitting, and the matrix is defined in the kind of Hilbert space dimension for the state vector. And we will take a simpler case. Generally this matrix one may have to deal with, and that matrix may not commute with each other as we go from one point to another point. So, more complication arises, which is called non-abelian connection. But what we will do is that we will assume that these matrices only have diagonal elements. So, that means they are defined for each states, energy states, or eventually for each band. If I have a degeneracy, then we have to deal with the non-abelian case, but let us assume that there is no degeneracy. So, we are talking about an abelian connection. So, it is only finite when n equal to m. So, only the diagonal terms, otherwise it is 0, off diagonal terms are 0. So, that makes things simpler. So, what we will do is that now you have only a delta mn. So, that means only the nth component survives. So, we can now combine all these things into taking the n summations outside. So, we will have this term plus this term, and I can take these two terms out, the psi becomes common. So, I will have delta mu plus a mu for n, and this entire thing we called covariant derivative on the function. So, you see now the covariant derivative is acting only on the function. As I said, this will only define on the horizontal space. All the vertical space derivative information is now putting in the horizontal space, and that is how a covariant derivative it is. So, it is the connection which keeps track of how the fibers are changing. Okay. So, it is a derivative operator that depends on, but now it is an interesting thing. It is a derivative operator, but it is not completely general operator. It depends on the state or the fiber that it is acting on. So, that is what this n index is also. Okay. So, this is the directional derivative we just defined, in which we take the fibers the change of the fiber as a connection, and this is my covariant derivative. And now what we will do in the next class, we will take examples, as well as we will intuitively say what it is actually doing on the fiber, and then we will define parallel transport and curvatures.